welcome to Scilax, the podcast where we talk about scientific developments and technological changes, very often in Luxembourg, but today it's not the case. Today is a Scilax original, which means we have an international guest, and our guest today is Professor Ignacio Cirac, who is a Spanish theoretical physicist and a director at the Max Planck Institute of Quantum Optics. Ignacio's field of research is quantum information theory. With his collaborators, he introduced the first proposals of quantum computers, simulators, and repeaters with atoms, and a lot of other important research in the field that I hope to at least touch upon. Ignacio, thank you so much for coming today.
My pleasure. Thank you for inviting me.
All right. When I was preparing for this, I kind of realized that it's not the first time I'm talking about quantum mechanics or quantum physics or quantum computers. And I have a feeling that anyway, I always start with the beginnings. And I wonder, do you think we really have to start with it? Are these all still terms and ideas that people don't understand and we have to explain to them? Or where is the threshold in general when we talk about general public?
Oh, I think that the threshold is very low. So I think that people don't know and they're scared about quantum physics, and there is a reason for that. And so it's better just to start very slow and from the beginning, and then one can see that if everything goes well, then there is not such a big problem, and there's no problem accepting that quantum physics will change our technology in the future, and we do it in a very natural way.
So you said people are scared. I actually recently was talking to a physicist who specializes in soft matter physics, and it was a completely new world to me. Of course, I know a little bit about liquid crystals because of the applications, but all the rest, the elastomers and everything, it was just completely new. So of course, I was not scared because I've never heard of it, right? Whereas here, we kind of talk more and more, right? So I would assume that maybe we are less scared, but it's true. The moment you say quantum, people start shaking a little bit.
You see, one of the reasons is that if you're working in a different field, like in medicine or what you mentioned, soft condensed matter, if I want to explain you some phenomenon or something that I'm doing in my lab, then I can make an analogy. So I can say, oh, this is like when the cars goes on the street and then there is a traffic light and then everybody understands it. Now for quantum physics, we have a problem. The problem is that these things don't happen. The things that happen in quantum physics don't happen in our surroundings. So we don't have an intuition for that. And therefore we lack the possibility of making analogies. And that's what makes it more difficult and also more scary because say, well, there's nothing I can compare to. So how can I understand it?
Okay, so let's try to develop a little bit of intuition of our listeners today. And as you said, we have to start from the beginning. So what are quantum computers? Let's start with that. It's not exactly beginning, right? But still.
Well, these are computers, first of all, that they don't exist yet, but that people are trying to build. And they would solve problems that computers can solve. So that's no different in whatever they can solve, whatever they can do. The only thing is that some of these problems, they can solve them much faster than the standard computers. And the reason is because they work with different principles. So they are not based on, let's say, semiconductors, transistors, and things like that, the kind of equipment that is in our normal computers, but they are built based on different laws of physics, the laws of quantum mechanics. And this is why they are called quantum computers. And also these laws of quantum mechanics are very different from the ones that computers use. And this gives us new capabilities.
But I thought that there is some theory with semiconductors and quantum computers as well, to apply them too.
Yes, but in a completely different regime that the semiconductors work. So if you open up your computer, you will see a lot of semiconductors. But they operate with different laws. So quantum computers exploit these other laws of quantum physics, and this makes it possible to do things that are impossible with the normal computers.
And the second thing you said that confused me, you said that the computers don't exist yet. But I did see some documentaries where they were actually showing physical things, like at the IBM quantum computer, standing there with all the coils and everything. Well, that's not a quantum computer?
Well, it depends on what you define as a quantum computer. So I would call them prototypes of quantum computers. It's like maybe in the 50s or the 60s when they wanted to go to the moon, then probably have some prototypes and they try some rockets here and there, but it was not possible to build one that would go to the moon. And it took some time, and the situation with quantum computers is similar. So you have prototypes. Some of them show that things work. However, these are not the ones that we want to build because they have errors, they are not powerful, they don't exploit all the laws of quantum physics the way that we want it, and this is why we are still building them.
So as you said, they are based on quantum, by the way, quantum mechanics or quantum physics? Is that the same or not really?
It's the same. It's the same.
Okay, good. Because I always wondered why it's already complicated. Why introduce two terms? But fair enough. So we have these laws of quantum mechanics in there, and it means that we are not looking into bits anymore as in computers, but we are looking into qubits. So what are they actually?
To answer this question, I have to tell you that there are a couple of laws in quantum physics that one has to take for granted. So it's not that they have an explanation. These are laws. It's like I tell you, things fall. Why do they fall? There is gravity. Why is there gravity? Because things are like that. So the same thing happens with quantum physics, and quantum physics tells you that when you're in the microscopic world, not in our world, but we really go to the very, very small things, then the objects start behaving in a very different way. And so one different object may have one property that is not really defined. So typically we say the position. So we are used to the fact that when you say that the particle, an object is here, it means that it's exactly there. However, when we go to the microscopic world, it turns out that the particle is not well defined. So even the particle knows where the particle is. So it's in different places at the same time. So that's related to what we call uncertainty principles and so on. But that's a property of nature that only when you observe, then the property is defined. Okay, so the property when you don't observe is not defined. So it's doing like many things at the same time. And when you look at it, bam, then it's defined. And that's exactly what a qubit does. It's like a bit, namely a system that can take two values, 0 or 1. But it can also take the two values at the same time according to this law of quantum mechanics. This is why we call quantum bit, because it can not only be in 0 or 1, but can also be in both at the same time.
But how can we apply them if they are not really in one place until we observe them? Because my intuition tells me that, okay, if we need a computer, we need to contain those qubits. And somehow I have a feeling that if you contain them, you're almost observing them.
Yeah. So first of all, they don't use this property of position. They use some other property. Like, for example, these small particles are like magnets. And you know that the magnet can have the North Pole pointing up or pointing down. And this is what would be a bit. You have a magnet and it points up, then you'll say it's a 0. And if it points down, it's a 1. But according to quantum physics, then these particles that are like magnets can be at the same time in 0 and in 1. So the position is well defined. So there's no problem with the positions that they're located somewhere. But that's another property, the one that can be in these so-called superpositions. And these are the quantum bits. Okay. So again, so the positions are very well defined. So they are there. Now we control them. So we make them that they don't, lost these properties. They're well defined, but it's the other one, the one that we exploit, this magnetization that we call it, the fact that it's like a magnet.
Okay, and then we're talking also about trapping them somehow, right? Because one of the ideas of how to develop quantum computers is to use the theory of trapped ions, like in the atomic clocks, right?
That's right. So now there are different incarnations of qubits. Okay, so you go to our labs, you will see some incarnations, which will be based on atoms, and some other places will be ions, and some other places will be superconductors, or there's photons. And now you go to the case of atoms and ions, then what you have to do is first you have to we have many atoms surrounding us. So there are like millions and millions. So you have to get rid of all of them because you want to have like 10 qubits or 20 qubits. You have to just get 10 or 20. So you have to take a vacuum cleaner, and take them out and in a small region of space. And then in that case, you can have these atoms or the ions that are only 10 left. The second thing is that these atoms weight, so they will fall. So you have to levitate them. And so for that, we use electromagnetic fields. So we use technology that is very well developed. In the case of the ions, they are charged. So they are like little charges. So it means I put in some electrodes, they will repel them and they will make them levitate. So at the end, we end up with a set, let's say called a vacuum chamber, where we have made the vacuum. We have these 10, 100 ions, one next to each other and levitating. And each atom contains a little magnet. And in this magnet is where we store these quantum bits, these qubits.
One of the things that was surprising to me when I started reading more about quantum theory, quantum physics, was that actually vacuum is never really empty. So what is the guarantee that in this vacuum with those few qubits, you actually really only have those few qubits?
Well, because vacuum means different things in different contexts. So when you hear things that the vacuum is not empty, it's because in vacuum, there is electromagnetic field, there are electric fields, and there are magnetic fields. So you have always superpositions of electric fields. So you cannot have exactly 0 electric fields, which will not be electric field. And it's related to that. Now, the vacuum I'm talking about is just the absence of particles. It's very simple. So you can count how many particles, and if there is 0 particles, a vacuum. If there is 1 particle, it's not perfect vacuum. So what you do is that you get rid of everything, and then you leave 10 or 20, and then there is no problem with the rest.
Okay, but it's the 10 or 20. So I'm picking on you again with what you're saying, right? This is a problem, right? We can't really scale it very easily, can we?
That's right. Now, depending on the platforms, and there are better ways or worse ways to scale them. So we would like to have bigger quantum computers with many of these qubits. And so in the case of trap ions, they have of the order of 100. And it's very difficult to get more. And the reason is because these ions are next to each other. And so you build more and more and more. They will have to make a vacuum in a very big chamber. And we don't have these chambers. We have to develop. Now, in the case of neutral atoms, these are like ions, but they are not charged. And then it's simpler. So people have already 400 or 500, even 1,000 in some labs in our institute. And the reason is because you can put them in 2 dimensions. So you can just put them like in a plane. So one here, then the next in the next row, and another one in the next row. And then you can have many of these rows. And then there's a better way of putting these atoms. And this is something that we know how to scale better. And if you talk about superconducting, it's much simpler to build them. You just have to write them on a chip, and we have some methods of doing that. And then this is why there are different platforms. And regarding scalability, some of these platforms, superconducting, are better than the other ones. However, they also have their drawbacks. So for some of the things, they are worse. And that's why, we have different technologies in which we are developing in parallel quantum computers, and it's still not clear who will be the winner.
So before we talk about different technologies, we expanded a little bit more. I think it's a good moment to ask the pub quiz question that you prepared also on the subject of qubits. So if you can ask the question right now, and listeners, remember, answer only at the end of the podcast.
As we probably will mention, the quantum computers, once we build them, then they will be able to crack all the encryption methods that we have nowadays. So this means that our messages will not be longer secure. And so now I talk about qubits, few qubits. And so the question is, how many qubits are required for a quantum computer to crack all the messages, secret messages that we, the banks, the government are sending nowadays?
Great. Of course, more or less, right? We're talking science, so it's approximate, but for sure. Yeah. And it will be interesting because as we are now saying how many we are able to have, right? We will know whether we are there or how far we are. So listeners, remember the solution only at the end. But now coming back to those different ideas of quantum computers, when you read all the descriptions of what you've done and whatever, you're put as one of the pioneers, persons that started thinking about quantum computers, had ideas. So let's start with your idea of how you wanted to develop the quantum computers. Where is it right now? So how far behind or how far ahead are you with the theory for quantum computers?
Okay, so this was developed about 30 years ago. And so at that time, it was not even known if a quantum computer was possible. And so the idea there was to show that indeed it should be possible to create a quantum computer. So we proposed together with Peter Zoller, so how to build quantum computers based on trap ions. And so the first experiment with trap ions had 1 ion, and then they did some demonstration. This was back in 1995. And now, as I mentioned, they have of the order of 100 ions. That's the state of the art. Now, we later on, together with Peter Zoller also, so we propose, and with some other people, we propose how to do quantum computations now with neutral atoms. This was a bit later, 3 years later, or 5 years later. And now I mentioned that there are 400 of those kind. So that's where we are.
Okay, good. What about the competing technologies?
Okay, the competing technologies, so the most important ones are superconducting qubits. That's what, for example, big companies like Google, IBM, and others are using. And they have the same order of magnitude. So Google has of the order of 100, IBM has 400. What is important to know about quantum computers is that at the moment it's not only the number of qubits that matter, but also the quality of these qubits. You see, in my glasses, there are millions and millions of atoms. So I have millions and millions of qubits, but if I cannot control them, then it's completely useless. So it's how many you have, but also to what extent you can control them and do whatever you want. Can you create these superpositions? Can you manipulate these qubits? And now that's the second number, which is different for different technologies. There, for example, the trap ions is the leading technology at the moment, where they have like the best control. And cold atom superconducting are lying a little bit behind, but just a little bit behind. And so that's why there is not a clear, let's say, front runner in this race. But it may happen that now all the technology is photons. So with photons, may happen that somebody comes tomorrow and has 400 qubits, and they're much better.
or something completely different as well, right? Just like lasers or other, technologies where we just discover them and we don't know what to do with them. So there might be some alignment in something else that you haven't even thought about.
This is indeed what happened with the standard computers. With at the beginning, they didn't look the way that they look like now, but then people discovered transistor was a discovery that revolutionized the classical computation or standard computation and made it possible to scale them up much faster than it was anticipated. So the same thing could happen with quantum computers. I mean, we don't know what its technology is. We don't know it will happen, but we cannot promise that it won't happen.
When you talked about those competing technologies, you said that this is important to know how many superpositions you can create. But I don't think we actually explained what superpositions are. So maybe let's circle back a little bit and tell our listeners what that is.
Okay, so I mentioned before that in the microscopic world, when you have a property, let's go with the one with a magnet. Okay, so you can have a magnet, which is a north pole pointing up or down. This is 0 or 1. And according to quantum physics, it can be in a superposition, meaning that it's with both of them at the same time. And that's where I cannot make an analogy. So I cannot have like a real magnet is at the same time pointing up and pointing down. But in the macroscopic world, it turns out that as long as we don't observe it, then these two possibilities exist at the same time. And only when we observe, then one of them disappears and the other one is the one that remains. And so we call those superpositions. So things that the property is not defined. It's doing several things at the same time. And that's what the qubits do. And what quantum computers exploit to do things that are not possible without superpositions.
And when we talk about quantum computers, we of course think of sending information as well, just what the computers do, right? Processing information, sending information. And the moment we're not really sure how we can control the errors, we have a problem, right? So how is it going, the error control side of things?
Okay, so this was several breakthroughs during the last year. So we knew already for many years that it's possible, at least in principle, to control the errors. We call correct the errors. Maybe one should explain that since we are talking about the microscopic world, then, we have to go there and we have some technology, but this technology is not perfect. So we cannot do the same things like here. We cannot just take something here and put it there. So there are some errors. And now the quantum computers suffer from these errors. And this is why we cannot scale them. So at some point, there are so many errors that are completely useless. And this is why we have to correct it. We know the theory of quantum error correction. We know how to do in theory, but in practice, it's very difficult. However, last year in several places, people were able to demonstrate error correction. And what is more important is to correct errors. And at the same time, they corrected errors, then they were not producing more, because in principle, when you correct errors, you have to do something, and this creates more errors, and so the balance is negative. So it was for the first time, let's say, positive and showing that they are better corrected.
It's still difficult for me to actually imagine the whole process. So error in this case would be what? That we caused those qubits to be a 0 or a 1, if you want? Or is it that we tried to measure them somehow and then, of course, everything kind of fell apart? Or what is actually an error in quantum computing?
No, an error it's very, very simple. So you remember that I told you that these qubits are in superpositions, are in 0 and 1 at the same time. And this is what we explode. So without superpositions, quantum computer would be like a normal computer. So we need these superpositions. But now imagine that somebody looks at the qubit in the middle of the computation. They will destroy the superposition, because I say that when you observe, you destroy the superposition. But it doesn't have to be a person or an animal. It can be just a molecule that goes by and crosses and collides with it. When we make the vacuum, that's not perfect. There are always some molecules there, and some of the molecules might cross and somehow read the qubit or observe the qubit, and then the superposition is gone. So it has created an error. That's what we call an error correction. And as you're making putting more and more qubits, then it's more likely that there will be a molecule that will produce some error. And that's where it's more difficult that there are no errors. But the solution to that is to have this correction of errors. So somehow, whenever something happened to your qubit, then you have some other qubits around that tell you that something happened there. And then you go there and then you correct and restore the superposition. That's the idea of error correction.
It means that in the future, when we will have all these compilers and people writing code, we will not talk about the debugging, but demoleculing or whatever else, right?
Yes, but this will be done by the hardware. So that's or by software, like a low-level language. So I think that programmers don't have to care about that. I mean, for them, if we build the computers we want, there will be no errors because they will be corrected and they will have to use it as if there was no error.
But still, we already mentioned programmers, I think as we're talking about computers, we need to look into algorithms. So how is this side of things? How many quantum algorithms do we have and where are we?
Okay, so we have very few algorithms. And so I can tell you the ones that we have basically, and there are 4 families of algorithms. And so these algorithms are for some problems for which quantum computers using the superpositions can do things much, much faster than the standard computers. And so these quantum algorithms are for certain problems. And so one kind of problems are related to some mathematical operations, solution of some equations, some difficult equations. And one example of that is what we call a factoring problem. It's a problem that has you give me a number, 21, and I have to find the 2 numbers that multiplied give us 1. 3 times 7 is 21. So problem of factoring and many other problems are very difficult for standard computers. So 21 is not difficult, but if you put 1,000 digits number and you want to factorize it, it's extremely difficult and it would take the age of the universe with any standard computer. Whereas with a quantum computer using superposition, we know how to factor much faster. So that's the first set of problems, some specific problems. And the main consequence or main impact of these problems is that our security in exchanging messages nowadays is based on the difficulty of these operations. So as soon as we have quantum computers, then these operations are not difficult, and therefore they will be able to crack messages. And that's the connect with the question that we asked at the beginning. Now, second kind of problems is to solve problems that appear in quantum physics. Okay, so when you have a quantum physics problem, like in high energy physics, in material science, or even in chemistry, then these are, you have to make predictions about objects that follow themselves the rules of quantum physics. And then we know that if we want to make predictions about those systems, it's extremely difficult, especially if we put more and more particles. Just to give you an example, you have molecular reaction where the molecule is composed of many atoms that come together. Just to solve that and to simulate with a classical system is extremely difficult, and most of them, even with supercomputers, cannot do. But that's where quantum computers can help. Again, using the superposition, then we know very well how this can be done very efficiently, and you will be able to solve problems that otherwise would be impossible with standard devices. Now, the third set of problems are related to optimization. And optimization is some kind of problems that appear very often in industry, and that's why the industry is interested in quantum computers. And so just let me give you an example of optimization, which shows where these optimizations are important for the industry. So imagine that you have a logistic company that has trucks, and they have to go and give some goods in different places. And I give you that they have to go through Europe, and it has to go through, let's say, 100 cities. And I know what is the distance between the cities, and I would like to go through all of them to give the goods there. And so the goal is to take the shortest path of all of them. And now you could start with one city, go on to the next one. And there are so many combinations that at the end is very difficult for classical computers to find what is the optimal one, or the one that you will save in oil or whatever. And so this is a typical optimization problems. And there could be optimization problems now industry, how to optimize some process in the industry to have it faster or more economical. So they appear very often in companies. And we know that for these kind of processes, the quantum computers can also help. Again, using superpositions, we have algorithms that are able to solve them. And the fourth kind of problem are related to artificial intelligence. And so we're now very familiar with artificial intelligence. And then we know for some specific problems, some problems that are not so important, but specific problems that quantum computers can also accelerate the classification of data, the data analysis, and so on. So altogether, these are the 4 families of problems where we know that quantum computers can help. But I think that the most important is that for the other problems, it's not that quantum computers don't help, it's that we don't know. Okay, so now nobody has figured out how, using these properties of quantum physics, it can help to solve the other problems. But we have many hopes that there will be many problems that will benefit from quantum computers. But however, we cannot say that because we don't know.
So we'll not ask you what kind of problems there will be because we don't know, but which of these applications actually make you the most excited?
I mean, for me, the most excited is that the simulation of physical system, the solution of quantum mechanical problems. So myself, I work on quantum physics, and there are some problems that I cannot solve with my computers. And so I hope that these computers will help me. And this will help us to advance science, but also some technology related to material and chemistry and so on. So I think that it's very clear that at the moment that's the application where we know very well that quantum computers will be very useful.
So we talked about the errors, we talked about, taking care of the superposition and being perfect and whatever, but how do you also make those qubits interact? Because that's also probably pretty tricky, no?
Yes, right. So the idea is that we have to create these superpositions, and it's relatively simple to have one qubit and create a superposition of 0 plus 1, like I mentioned before, or 0 and 1. And this is done just by addressing, for example, with the ions lasers to each of them independently, and each of the qubits will do something. Now, the problem is that that's not enough for quantum computation. As you mentioned, for quantum computation, the qubits also have to interact. So you have to carry out 2-qubit case, we know, in which 2 qubits, they behave in some special way. And for that, they have to interact with each other. And now, depending on the platform, this occurs in a different way. In the case of ions, the fact that they have charge, they make them interact with each other. So if I move one ion, then the other one feels it. And we can use this effect in order to make the quantum gate.
But then what I understood is that in case of trapped ions, we are talking about cooling them, right? So slowing them down. Didn't this slowdown actually influence the interaction as well?
For ions, the first thing that you have to do is to trap them, as I mentioned before, to make them levitate. But then these ions are moving very fast. So because, they're at high temperature, so we have to indeed cool them because we want to have them at a certain position. So we want the qubit is somewhere and doesn't go away. If it would go away, we would not have a quantum computer. And so for that, we have to cool them. And so cool means to stop them. So they're moving very fast. So actually an ion, when it's trapped, it has a speed which is the same as like a airplane. Okay, it's huge. And so we have to stop it, and basically to stop at 0. The ions cannot break, so we have to make them break, and we do it with lasers. And the basic idea is that the laser is composed of photons, and these photons push the ions. So the photons is like a bullet, and so the ions, when it moves, you put some photons against it, then it will stop. And so this is how we stop these ions, how we cool them. And so we cool them in such a way that now they're in particular positions that they basically don't move. And once they are there, then we start with the quantum computation. So we first cool them, we'll trap them, cool them, and then quantum computation. And quantum computation, as I mentioned before, we make them interact, we interact with lasers and so on in such a way that they perform the algorithm that we want to do with them.
Cooling is basically the state that you are aiming for.
Well, it's just trapping and cooling. Also, there are some details. So you have to put this, if you want all these magnets, these small magnets, which are the atoms, you have to put them, all of them at 0. So it's like when you take your pocket calculation, at the end you have it 0. You start calculating with a number that is random, there will not work. So you have to initialize them. And that's very simple. Also using lasers, we know how to put them, all of them in the state 0 without superposition. So, and then once they are there, then we can start.
And is it important which atoms they are?
Yes, it's very important because the atoms now react to photons, to lasers, in very different ways. So there are some atoms that some photons that correspond to the yellow color stop them, but the reds don't stop them. And some other ones, which is the other way around. And now we have lasers that have only some colors. So we cannot use every atom because we will not be able to manipulate it or to stop it. So we have to match now the atom or the ion with the lasers that are available and see what are the best ones. And also, these ions, while these magnets are up or down, then it turns out that they sometimes tend to have an error, even if nothing crashes with them. And so we have to take the atoms for which these errors are small. So there are many details, and this is why there are some certain atoms or ions that everybody are using. The periodic table has 110 or whatever number of atoms, but we use only 5 or 6 because these are the ones for which we can cool them, we can trap them, we can manipulate, we can make them interact, and so on. They fulfill all those conditions. Typically, one trap ions quantum computers, they will have at most 2 kinds of ions. So one of the quantum computer, and some other ions may be there to help. and sometimes they are useful. And the reason is because maybe as you're doing the computations, they are heating up, so they start moving and moving and moving. And at the end, if they move too much, then the computation will go wrong. So what you have to do is to stop them. However, if while you're doing the computation, you try to stop them, then you will make errors. So you cannot stop them. So this is why you have some other ions that are there, what is called sympathetic cooling. So what we do is that we cool these other ions. This doesn't affect the quantum computation, but the fact that they are getting slow, they are also helping the other ones to slow down. And this is how we help them to be cool during the whole computation.
It's like with yawning. One person yawns, the other does too.
Yes,
right?
yes, very much. Yes.
I'm trying to find at least some, analogies, because as we said, it's not always very easy with quantum mechanics or physics to know the exact analogy we could use.
Well, yes. Well, it's like, or in traffic, now the ions are moving, and then you start putting tracks there. So the tracks will stop the circulation and they will move slower, and these tracks go slow, then they don't let things pass. And so, for that, I think that you could have some analogies.
True, exactly. What I was wondering as well, I can personally say that I understand it way more right now that we discussed it. But I was thinking, okay, let's say in 20 years' time, we have quantum computers. Do you think people will need to understand how they work to use them? Because, looking at the computers right now and chips and putting the sound card or whatever right now, I don't think people really know what is inside the computer. They're just using it, right? The same goes with coding. In the past, you had to know how to program. Right now, you have all the assistants that you can use, and it's kind of becoming really way less hardware oriented, let's put it this way. So what about quantum computers?
First of all, to be a user of a quantum computer, you don't need to know how quantum computers work in the same way that to use a cell phone, you don't need to know how the electromagnetics wave work, or to use a classical computer, you don't need to know how transistors operate. So that's not necessary. So quantum computer for you could be a black box where you do something and then something coming out, and that's what you're interested. What happens in between, you don't care about. That's a product, you don't care. Now, to program these quantum computers, then there will be different level of languages like there exist for classical computers. So at the very low level, then of course you have to know a bit of quantum physics, but nobody will program at the low level. So you'll have compilers or something in such a way that you can go to a higher level. And at the end, this is like a subroutine. So you call a subroutine in your program, and this does something, comes with the outcome, and you don't care about what happened there. So in fact, it makes sense to think that a quantum computer will be even a part of a standard computer in which you only call the quantum computer whenever it's useful. Otherwise, you just use the normal computation.
So to finish off, maybe one definition that I don't know whether we will have to understand when one day we'll be hoping you will be able to explain it to me, because I was actually watching one of the podcasts where you're talking with Peter Zoller about all the developments. And I have to say it was pretty hardcore for a person who is not a physicist to understand what you're talking about. And you talked a lot about the quantum gates, right? So the quantum logic gates. And I was wondering, okay, this is one of those terms.
Okay, so let me first explain it with a classical computer, so that let's leave aside the superpositions and so on, just to make it. So when you have a computer and you do your tax declaration, then you have to put some numbers, and then these numbers will be processed by a computer, and then you get the outcome, which is how much you have to pay for taxes, right? And so there is an operation taking part, and this operation occurs in a way that, first of all, every input that you give is translated into bits. It's a language, okay? So you have an A is 0000, is a B 0001, and so on. So you have bits there. And now, in order to get out of the input your output, then you have to process the information. So this means that now you have to take 2 bits, and if they are in 00, then you produce another bit which is in 0. And if they are 01, maybe you produce 1 is in 1. Then it takes the next bit. And so this concatenation makes the program that at the end gives you the output. And you see, it was shown many years ago that actually you don't have to make that all the bits interact with all the bits in order to produce the tax declaration, but you can do it in pairs. So you can do like take 2 bits and do something with them, then take another 2 bits and do something that, and we call them gates. And so the bits through gates perform the computation. Now take a quantum computer, it's the same. Now you have qubits, and any computation that you have to perform can be decomposed into 2 qubit gates, meaning that you'll have to take 2 qubits and make them interact, and some other qubits and make them interact, and anything that you want to do can be done like that. And so that's the concept of quantum gate.
Clear.
Okay.
Easy peasy. I think the Wikipedia entry was a bit longer than your explanations. I'm sure there's a little bit more, but thank you for making it clear. If people want to know more, they will definitely read more. And I think you can feel by now that it's a little bit of a wrapping moment. If you can remind our listeners what the question was about, and then, of course, let's solve it.
Right. So I mentioned that one of the most impactful applications of quantum computers that they could decrypt all the secret messages that were sent nowadays. And so how many qubits does a quantum computer have to have in order to be able to decrypt the messages that we are sending nowadays? And so the number is approximately 5,000. So we have 400. It's not that far away. However, and that's the important point, there shouldn't be errors. So first, we have to make sure that there are no errors. And then if we have 5,000 qubits without errors, then we will have this application. And so that's something that will not happen in a year or two because we have many errors and we have to correct. But it may happen in something like 5, 10, 15 years in which we are able to scale up, correct errors and have 5,000 qubits. And then in that particular situation, then our life will probably have to change because we will have to change all the ways in which we communicate.
But it doesn't mean we are not trying to do it already, right? I mean, there is the whole idea of quantum safe communication, and then we're sending some things. What do you think? Who's going to be faster?
No. Now that's the idea that people realize that, of course, if quantum computers take 10 years to be developed or to be built, and then we should prepare ourselves now. And for that, we should change the methods in which we do cryptography and to try to protect them with respect to quantum computers. That's what is called post-quantum cryptography. However, one has to say that this is secure, but to some extent, because as I mentioned before, we don't know many of the applications of quantum computing. It's not that they don't exist, but we don't know. It may happen that one of the applications is to decrypt the new post-quantum cryptographic methods. And in this way, then we will have problems.
Okay, so I don't want to stay very, very negative at the very end. So I think I wanted to mention one more application that, who knows, maybe will happen with the quantum computers, which is the theory of quantum gravity. What do you think? Will the quantum computers help with that?
I mean, I'm not an expert, but I think that that's something to say. I mean, there's some theory of quantum gravity and some conjectures and some questions that we cannot answer because our computers are not powerful enough. And so probably with full-fledged quantum computers, we'll be able to answer these questions. And this will definitely help us to develop science. I don't know if they will solve the problem of quantum gravity, but definitely will be a tool that we'll have on our table that will help us to do research. And in this particular way, I think that it will help probably a lot.
It's always the big question, right? We sometimes, especially nowadays, unfortunately, with the current political situation, we discuss a lot science funding, right? And the situation. At the same time, I liked, I think in one of your interviews, maybe you or maybe someone else was saying that, yes, funding is important, but it's also the time and the ability of people and the brain power that they have to actually develop the theories further, right? And then the question is, will quantum computers in this case, or maybe supercomputers and their abilities of calculating certain things help, or do we really need the right human beings to come up with the solution?
Well, we will need both probably. So I don't know what will be the proportion. And even things related to artificial intelligence and machine learning can help in that, and quantum computers and whoever. We think that human beings, we are trying to make progress in science and technology, and we can use whatever it's at our disposal. And these things are coming, and so I'm sure that they will be useful to develop not only applications for society, but also feedback in science and advanced science.
Okay, and now it's a little bit more positive. I like that. I don't like finishing with a bit of a negative outcome and outlook on the world. So thank you very much, Ignacio, for today. And listeners, if you're interested more in physics, I'm actually also starting a new series where there'll be even Peter Zoller, also one of the guests. So I'll be sharing all the notes and all the links to that. You can go and listen to these interviews. And once again, thank you very much, Ignacio, for today.
You're welcome. Thanks.
And this is it for today. Don't forget to subscribe, to follow us, to check what we're writing on all the social media. And of course, don't forget to suggest guests as well. This was Silax, and my name is Hanna Siemaszko.